So this is a series which I started last year. There's 7 in this series, so this is number 4. And for those who haven't joined before, it's all about giving you some tips and tricks in designing electronics. So say this time it's going to be all about operational amplifiers. There's a few explanations, a little bit of tiny bit of maths behind it, just some of the useful equations. Not doing any derivation. It's just here are some equations that go with this, and of course some experiments. And you will find a lot of stuff online if you look on YouTube. So really what I'm trying to put together here for everybody is something that complements that. So it is more practically orientated, and it can go to a little bit of a deep level, not too deep. It is live. So as I say, anything can happen. And my name's Stephen Clemmet, as you probably may know, and I've been doing this for 27 years now. Can you believe? So op amps, right? So first thing I'll say is that they're very commonly your operational amplifiers. There we go. I'm saying it already. They're very often just abbreviated to op amps, which I think is nothing short of just being slightly lazy on the full name. It is a massive subject. And I think we'll be lucky if we can barely scratch the surface of that this evening. So we'll look at some concepts that I use regularly as an electronics engineer. So where to start? Well, I have got off my shelf a very early operational amplifier. There it is. Huge. The data sheet for it, I forgot I had this one. So this is actually 1948, this operational amplifier. They were a little bit big then, although it does say here.
Hello, I've just been delivered an order using.
Ruth, do you want to turn your sound off? Sorry, Ruth. Yeah, so this says this is small. So this is an early one. These days, they tend to come in bags, and we'll have a look at this in just 1 second. And you know, these days they are roughly, not sure where you can see this, they are as small as that black dot, which really is a bit of fluff. So there you go, 1948 to 2021, they certainly shrunk in size, I would say. So just put that to one side, shall we? So they've been around a long time. I actually did a bit of digging to when the first one was invented, and I think it's 1941. So they've been around a long time. They only actually became chips, you might be interested to know, in I think something like 1967 or 68. So yeah, been around a long time. And the basic principles have not changed. So I thought maybe the place we should actually start is, how do you choose an amplifier for a circuit? I had a quick look on DigiKey. There are currently over 40,000 of them to choose from. So where do you start? So I've got just a little tiny checklist here. These are the things that when I'm choosing an op amp for a circuit that I have in the back of my mind. And this top one here says rail to rail. That means that the input voltage you apply to these electronic devices, which we'll have a look at in just a moment, can be from the minimum voltage rail, let's say -3 volts, all the way up to +3 volts. That's what we mean by rail to rail. It can actually hit the supply rails. Some of the very early ones, 741 is a popular one that we all started with in the 70s. And I started tinkering with this stuff probably in the early 80s. Couldn't get to the voltage rail. So you had to be a little bit more careful with the design. So I always tend to go, if I can, from rail to rail on the input and on the output. So that's a consideration I always have. So these are the parameters which I'm looking for when I think, right, how am I going to pick something? I think the operating voltage goes without saying. Some op-amps, operational amplifiers, can work on a single rail. That is, say, 0 volts to, say, 3 volts, 5 volts, 12 volts. And others will require a negative voltage. And the ones we're going to play with this evening are a negative voltage. I'm also looking at the current draw. These things, some of them will draw, you know, maybe a few microamps. And some of them, if you're doing battery operated, will draw a few nanoamps. So there really is, you know, a criteria which you just need to sort of drill down through to find, and you'll very quickly start to narrow that list. The bandwidth, that means what's the sort of frequencies can this thing handle? If we're doing audio work, you know, we're going up to, say, 40 kilohertz for audio. I think you'll find just about every op-amp in the world will do that. But if you're going to do radio frequency, 100 megahertz, then you'll start to be more limited by your choice. And the last thing on here, which I've said, speed, is how quickly does this device respond to a change in the input? And that's usually measured in volts per microsecond. So just very quickly, I don't lose too much time here. So when I'm looking, if you look on DigiKey or any of these others, you can find data. These are just some examples of some data sheets, which this is the one we're using this evening from Microchip. It's, you know, it's got our positive rail V plus, our minus voltage here for our negative voltage. We've got 2 inputs. We'll look at them in a second. And of course, it's got an output. And that's pretty standard. And they always tell you various applications that they're good for. Let me just see if I can refocus that. Is that any better? Maybe I'll bring it up here so you can all see it a bit more. There you go. Yeah, so look, so it's got all these parameters here, how fast it is. Obviously not going to get 3,000 volts out of it, but it's just a typical op-amp, what you could use. There's another one here. This is what I was mentioning, rail to rail. This draws, what, 500 nanoamps? So this is a perfect choice if you're, say, designing a battery-operated piece of equipment. And just the last one here, we're going to look at this one. This is called a differential amplifier. So we're going to look at this one in a few minutes in a bit more detail, but just to give you a flavor when you're looking at devices, there's a little criteria just to plow your way through, and you'll very quickly narrow it down to, you know, less than 100. So 400 down to less than 100 for a few button presses is not a bad effort. Right. Okay. So overrunning there just by a second or two. So let's have a look at our first experiment, which is brilliant. Right. The non-inverting amplifier, one of the most useful bits of kit. So this is a general configuration you'll find everywhere for, you have an input, which is VI for in, V0 for out, and the output voltage relative to the input voltage, you can have a gain. And this gain is set by these 2 resistors. So you can just set them to what you want. Usually I'm playing with resistor values of between maybe about 10,000 ohms and, you know, around 100 kilo ohms. That's the sort of range that I tend to play with. So can you see at the bottom of your screen a small oscilloscope? So on this oscilloscope, in fact, what I'll do for us, let me just swap this to make it a little bit easier for us to see. I sometimes have to think about this. Oops, I think I've lost it. Hang on, everybody. Let me just get that back. Sorry about that. Let's just reshare that. Right, I think that's back in the room. Right. Here we go. So I will share camera 3, I believe. There we go. That's a bit easier to see, isn't it? Right. So I've got a little electronic circuit here, which we'll swap back to in just a second. The yellow line, which is this one, this is our input. And this blue one, that's our output. Now they're both set to 500 millivolts per division. So this is an amplifier. This is a non-inverting amplifier. And as you can see that the output, which is this blue line, is in phase with the yellow line. So it's clearly a non-inverting amplifier. But here's the first limitation to be aware of. This might work if we're lucky. If I just change a couple of things here. Right, so this is the first limitation. I always like to do an experiment to show things can go wrong. So if we increase the amplitude of the input, that's the yellow one. Yep. If we increase it too much, you'll start to see it's starting to lose its waveform. So, and this phenomena, if you like, is called clipping. So the operational voltage of our device is running on plus and minus 3.3 volts. And we've got a gain of, I think, about 2.5-ish. And so if the input voltage rises above 1.5 volts, you can't have more output volts than what the power supply is generating. So we get a little bit of clipping. And the other thing I'll show you on here, if we just drop that a second, and we'll go to a higher frequency. Right, so there's our amplifier. If we look in the frequency domain, if I can get this to work properly, there we go, FFT. Right, so fingers crossed. So I've got this going at about 1 megahertz. Okay, that's up at a gig at the moment. Right, right, there we go. So you see that spike there in the middle. We can just move that to the middle. If I can move it, there we go. Right, so that red line in the middle, if you can see that, okay. There we go. So that red line in the middle, so that's the output frequency of the signal sine wave going into our op amp. But if I increase the amplitude, so it starts to clip, we should, and of course it never works when I do my demo. Usually you can see next to it, these other harmonics will start to pop up. I think maybe if I wind it down, it might disappear reasonably. There you go. Let's see, it's almost disappearing. So if you start getting clipping in your amplifier, not only are you distorting your waveform, you're also starting to introduce unwanted frequencies. So if you're doing some frequency analysis and you got clipping, you'd certainly start to upset your amplifier. And if you're doing some maths, for example, you start to upset it. So something to be aware of. It's not always as straightforward. Right, let's drop that back there. There we go. So there's our clipping. Right, okay. So that's a reasonably straightforward example for us. Just trying to, oh no, wish I hadn't touched that now, don't I? So because I moved that. No, that one. There we go. Perfect. Right. Okay. Got it back. Right. So let me share with you another type of amplifier I use. So let me just, oh, that keeps on unsharing as soon as I try and change the camera. That's not what I want. Bear with. There we go. Right, so that's a non-inverting amplifier, and of course there are limitations we need to be aware of. The next amplifier, which I tend to use, is a buffer.
Sorry, can I ask a
Yes.
question about that first one?
Yes.
Is that formula universal for all op amps?
Yes, it is.
Right. Okay, so that's not something from that data sheet. It's just
no. This is. I mean, I'm not going to get into derivations, but sometimes you'll see this R1 written as RF for feedback, and then that might be R1. Okay. But no, that's you'll find that written every single time.
Excellent, thanks.
Okay, brilliant. So it's a slight variant on that, which is a buffer. So you can think of a buffer as a non-inverting amplifier with a gain of 1. How do you make it a gain of 1? Well, if you make RF equals 0 ohms, and if you make R1 an open circuit, which is almost infinity ohms, 0 over infinity is mostly 0. So 1 plus 0, the output would then be the same as the input. So this one here is, it looks like, well, I could do that with a piece of wire. Well, of course you can. But the beauty of this is if you're taking signals off board, I would go through a buffer. Or if I'm coming inboard from external, I'll also go through a buffer. So it's just a way of making sure that you're preserving the integrity of the signal when you're on your board. And I do use it quite a bit in electronics.
What do you mean by preserving the integrity of the signal?
Really to make sure, yes, factually, the next slide will explain this to you in just a moment, actually. So let me show you on the next page, because that actually answers your question. It's almost like we planned this. So if we look at a inverting amplifier, that's when the output is the inverse of the input. And I can show you that here. Hopefully without losing the cameras. They seem to switch off every time I swap cameras. Right, so here, this is a non-inverting. Oopsie days. There we go. There we go. So that's our non-inverting, where the output blue follows the input, whereas for an inverting, it's the other way around. You can see they're actually 180 degrees out of phase. Yep. And we'll come to your question in just a second about preservation, because it's really, I use it mostly when I've got this inverting amplifier stage going on. So hopefully without losing the camera, this seems to be a bit of a popular theme this evening. There we go. So that's just on this little board here. I've just moving between 2 pins. I've got some different amplifiers on this board here. So for an inverting amplifier, and there's plenty of occasions when I end up with inverting, the ratio is this R1, sometimes called RF again, divided by this resistor, and of course it's minus. And again, as with the non-inverting, it's a universal, it's exactly the same equation, whatever op amp you've got. Now, to come to your question just a second ago about preserving the integrity of the signal. Here I've put a buffer circuit on the input. Now, the reason I've done that is because if you have let's say a microphone or some other power source which has got a small resistance, most power supplies have an internal resistance. It's usually it can only be like a fraction of an ohm, but if that resistance of a source is comparable to R2, R2 really becomes R2 equals R2 plus some small resistor from the source, which would then, of course, affect what the gain of your amplifier is, if that makes some sense. Yep. So that's why I tend to use it mostly certainly if I've got an inverting amplifier going on. Why would you use inverting over non-inverting? As I said, the earlier, we're barely scratching the surface of these devices this evening, and there's plenty of different configurations of op amps, where like summing amplifiers, logarithmic versions, integration, differentiation. So all the maths which we take for granted with our digital calculators, you can actually do them with op amps. But when you do a lot of them with op amps, often you end up with an inversion because this negative feedback. So you can't do a lot of these calculations with a non-inverting amplifier. They always generally wrap around a non-inverting amplifier. As I say, it's such a massive subject, just can't cover it all this evening, I'm afraid.
Stephen, are you going to cover where we get minus 3.3 volts from in our circuit? I'm used to thinking in terms of ground and V plus or VCC.
Yes, okay, right, okay, good spot. So yeah, so as I mentioned earlier, a lot of power supply, a lot of most op amps, I should say, require what we call a split rail. I mentioned that a little earlier. And yeah, so when I'm designing electronics, I tend to use like ARM cores, which are usually 3.3 volts. So it's kind of my go-to voltage. There's no reason why, if you look at most op amps, you can easily go up to 5 volts. Some will go to 12 volts. So it's just an arbitrary value. Yes, you could say on here, yeah, plus V and minus V. I just happen to choose 3.3 and minus 3. So no real reason for it, apart from when I'm designing electronics, say it's just my go-to voltage these days. Is that okay?
Yeah, the question was really about how I'm thinking in terms of a circuit where I've got a battery as my power source. So I've got kind of a negative end and a positive end.
Oh, I see.
Here you've got 3 voltage levels. If presuming your signal ground is halfway between your V plus and V minus.
Right. So okay, right. So to answer that question, so if we go back to the very first in the session on power supplies, I had a section in there on how to create a negative voltage from a positive voltage. So you go through a small chip. So in our board here, I've only got a 2-wire input here, just as you say, there with, plus 3.3 and 0 volts. How do I get minus voltage? I've got a small voltage inverter circuit on here that creates it for me. So you can't overload them. You won't be able to sort of draw lots and lots of currents from an inverter, but certainly not this small, like you can from like the positive supply rail. But if you're just running op amps and creating a reference voltage, as I see, I've got a tiny one running here. So if you go onto the onto my Silicon Cortex website to downloads and download the section on power supplies, and particularly the schematic, you'll find the design in there for creating this minus voltage just from a ordinary plus voltage power supply.
Thanks. I'll go back and do my revision from that session.
Yeah. You'll start to notice as we go through these these interactive sessions that there will be links to something we did earlier. So so the process which I'm putting it together, everything does sort of lead into something else for us, which is why next time we're doing sensors. Right. Okay. So the next one I often play with is called a differential amplifier. This is getting a little bit tasty now. So this is an off-the-shelf chip. It's this one here in the top corner. And the gain of it, and this is not so much universal now. This will be, the gain of these devices will be vendor specific. So I've got on So this particular op amp I've got here is an A128. So this is the one which I tend to use quite a bit. A128 works pretty well. Yes, it's running on a split rail, and the gain of it is just one resistor. So I've got it here, RG, and this is the equation that they give to use it. So for these differential amplifiers, you've got to go to the data sheet to get the answer. It's not a generic equation. So how they came up with that is all down to, I'm going to hold up to the camera a little bit and press focus. There we go. Look at that. That's nice. So the gain of these is given by the manufacturer. And of course, it depends on how they've actually made the chip in the silicon. So if I'm using or designing, let's say I've got an example here of, oh, let's all out focus, face soft focus. There we go. So with my design there we go, a little bit easier to see. So with this design here, I've actually got an infrared sensor. So if I drop that on there, and if I go to bring up the, I've just discovered this feature. It's camera 3. Right, so here's the oscilloscope output. Well, we don't need to worry about that this time. So if I just put my hand over it, you see the output increases. You can see that bottom right. Yep. I think if I do it with the soldering iron, it's even better. Only my soldering iron's unplugged for some reason. The cable's falling out the back. We'll worry about that. Yeah, so you can see, in fact, I could do it even better. There we go. Look. There we go. So you can see. So that's just so. But if you look at the data sheet for this sensor, which is here very conveniently, you'll see when you look at these type of amplifiers, they've got a very small, depending on the voltage, the temperature. I mean, in here it's about 16 degrees. So I'm about at this point here. Yeah, so I've only got about 0.5 of minus 0.5 of a millivolt coming off that amplifier, coming off that sensor. So using an amplifier, as we've been discussing, of just trying to find it, there it is. So if you've got a very small signal, using a non-inverting amplifier or an inverting amplifier might not be the best choice. You might need to, particularly if it's something like a temperature sensor, or let's say it's a microphone, for example, or maybe a piezo microphone, where you've got potentially a differential, 2 signals. You might. This is actually the infrared temperature sensor here. So you might be better off going for a differential amplifier. Now, here's a little wrinkle I've discovered recently, because I've been using this circuit for this sensor for another project. And what I discovered was, in order for the differential to work correctly, I had to add an extra resistor in order to give it a reference to work, particularly for this type of sensor, of a temperature sensor, where it didn't work to have the signal floating. It was causing me all sorts of problems. So it just seemed to make it work of just adding a large resistor to pull down one side. So it's then got a reference to ground, is probably what made it work. So that's just a top tip if you're using differential inputs. I learned that one the hard way. Right, okay, so another brilliant little device, the perfect diode. So if I pop that on here, and this one on here. Right, so if I increase that, there we go, we can make that nice and big. Right, there we go. So you can see in the bottom right-hand corner, this oscilloscope. So I've got a sine wave input plus and minus, which is my yellow line. And my blue is actually the output. And as you can see, this is a perfect diode. So there's no negative voltage coming through, and there's no voltage drop on the diode. Why do I use this circuit? I use this circuit if I'm going into, say, an ADC, or if I'm going straight into the analog device on either an Atmel chip on your Arduino, the analog input pin on your ARM cores, or your Raspberry Pi, where if you were to put a negative voltage into those devices or an ADC chip, you'd probably do it a power no good. So a perfect diode will solve that problem for you, and the output will follow the input. What I have discovered, a couple of things by doing this recently on a project. One, I found that if I added a resistor on the output, as you can see, it's just feeding back, it helped ensure that this diode was correctly conducting. So as just a little tip, just, this was 560, maybe a kilo ohm, just to start to make that device work properly. So I found that made a huge difference. The other thing I have discovered with these is on my oscilloscope is if I start to increase the frequency, this is when a demo will probably go wrong. There we go. Right, so there it is. So there's our perfect diode. I just set it above there so you can see that bottom right. If I start to increase the frequency, I've discovered that things start to go horribly wrong. And I'm going to go up to about 3 megahertz. Oops, this one here. Look, and now you can see I'm now getting a negative voltage out of it. And yeah, the whole waveform is starting to get extremely ugly. So look, so why that is, I'm really not sure. I haven't had a chance to look into it since I built the board a couple of days ago. But I imagine it's probably a characteristic of the diode. Almost looks like a sine wave going straight through now at a high frequency. But say as I drop the frequency, there you go. You can see bottom right on your screen, hopefully. It then starts to behave itself. There we go. Look, so now it's behaving itself properly again. So why that is, I don't know.
So it's an imperfect perfect diode.
It's an imperfect perfect diode. Absolutely. Yes.
I would guess it's something to do with the recovery time of the diode.
Oh, you might be right.
That's what I would guess.
You might be right. I did look in the data sheet to see if it gave any specification on frequencies. There was nothing there written at all. So
if it's a vanilla jelly bean, perhaps not.
Yeah, I mean, maybe if I got some other diodes out the drawer and had a tinker, I might start to notice something for sure. Yes, right. The last thing on my list here for us this evening, and this is very, very cool. This is a subject in its own right. Active filters. I think when we do season 2 after the summer. I'm keen to do this, a whole session on filtering, which is a fascinating subject, really. So this is, if anyone's got Horowitz and Hill, okay, I don't have shares in Horowitz and Hill, but if I did, I'll be brilliant. So if you've got Horowitz and Hill, if you haven't, go and buy it from all good bookshops and turn to page 408, they give you the most brilliant explanation on this Salonen key. It is so versatile. This is like the ultimate cheat sheet, in my view, on filter design. Now, the reason we use op amps for filter designs is you can probably see the one thing missing from this filter design are inductors. So by using an op amp, we can actually get rid of all the inductors. And there is a gain, it's 1.84 for this particular configuration. So different configurations do have different gains. So there are trade-offs. I don't know how they came up with these numbers, but just trust me, they work. And it's a ratio. It's not exactly 11, exactly 13. It's a ratio between the two, which must be, this is called a Chebyshev, this version. This version here must be, this gain has to be 1.84. So this is the non-inverting. So the gain, of course, is 1 plus 11K over 13K, which you will find is about 1.84 if you get calculators out. But for the filtering, there's a slightly different equation. 2 pi, that essentially means 3.14. When we talk about filters, I'll explain a little bit more about that. For now, just take it as this is a piece of genius. And then the frequency is these two capacitors and these two. So these two must be the same resistor value, and these two must be the same as well. And you can just rearrange this equation. I mean, if you wanted to, I usually fix C when I'm doing filters. So if I had times F, I could swap F and R there. Quick bit of algebra for us. There we go. And so I could work out what frequency I wanted this thing to cut off at, give it the capacitance, and it would tell me what resistor I would need. So no inductors. That's why we use them. And we can just see that working, fingers crossed. Always good to do a demo to prove these things are not made up. There we go. Right. So let's just change. Hopefully you can still see in the bottom right of your screen. So you can see our output is definitely, which is our blue line, is definitely larger than our yellow line, which is our input. But you can also see as well, and we'll talk about this another time, that when we had our non-inverting and our inverting amplifiers, they're either in phase or completely out of phase. Well, look, now it's neither. So, and the reason it's neither is because we've got capacitance in the circuit. So we'll look at that another time. But you do get a phase shift between the signals. But here's the magic. So this circuit here, this is essentially just, this is a filter. So high frequencies will get through. Oh, my cat's come to say hello. Go and run away. Go and play. So high frequencies will get through and low frequencies won't. So if we increase the frequency or reduce it, we might start to see this one here. Oh, there we go. Look, so there you go. So you can start to see, so in this filter here, there we go. Look, so the input hasn't actually changed. The yellow hasn't changed. But as I increase the frequency, there you go. Look, there's a slight change in the input, but not huge. It's just a limitation of the signal generator it's called connected to.
Can you make the oscilloscope full screen? It's very hard
to
see
for
this one. The others have been fine, but this one.
Right, absolutely right. Now, this is when it might suddenly switch off. So camera 3. There we go. How's about that?
That's good.
And I will swap that to that one. There we go. That works, doesn't it?
Yeah.
Sorry. There we go. Right. So to twiddle the right knob here. So there we go. So as the frequency, our frequency goes up, see, we're starting to lose our output. So this, using a op amp as a filter circuit, yeah, you do get gain. So that needs to be taken into consideration. But say there's no inductors. So you can make it cheap. And if you're going to very low frequencies, If you're doing, say, sub 10 hertz or something like that, sub 100, the inductors can actually get not only expensive and difficult to find, they also start to get physically quite large. Whereas if you use what we call an active amplifier and say it's a whole subject in its own right, it's cheaper, which is brilliant, and it's much smaller. And you've only got capacitors and resistors to worry about, so life just becomes much, much easier.
So here the output amplitude is decreasing as it's not like a sharp cutoff. It's a fading out.
No, brick wall filters are a myth. That they don't exist. Again, this is sort of second year degree stuff. The nearest you'll ever get to that is a filter called I think it's called an elliptical filter. That's as near as you'll ever get to a brick wall, on off. That it just plain does not exist. Everything in electronics is a compromise, of course.
So is there a kind of term for how broad that frequency band is?
Yes, right. So again, this is a whole subject in its own right. So just going back to here, so they've got a nice example here. So I'm just going to swap to back to, where are we here for us? Bear with. There we go. Right, so to answer your question. Right, let me just get rid of that. So there we go. Can you see that okay? Brilliant. So yeah, to answer your question. There we go. Right, so if you look, so you have what's called a filter order. So we just had a fairly simple one, but you can, as you can see here, you can start to cascade them together. And when you cascade them together, well, we get different types of filters. This one's called a Chebyshev, which is my favorite. Everyone's got a favorite filter. Depending on, these are called poles, which essentially, well, poles and zeros, which is complex numbers, the square root of -1. I'll share that with you another day. Try square root of -1 on your calculator, and it'll probably kick up an error. In electronics, it's fantastic, and I use it all the time for filters. But to start to get to that sort of brick wall sort of event, say it is a myth, you have to start to have more and more of these filters. So you start to cascade them. And so it's getting a little bit more complicated. Say this table here is just a whole bunch of magic numbers which don't deviate from, and it works. So they clearly spent a bit of time working this table out. But the net result is here. So as you add more sections, this is 2 of them, 4, 6, and 8. As you add more and more sections, you're starting to bring this roll off, which is what it's called, because it's rolling off. You're starting to bring that more towards the vertical. But you'll never get it truly vertical. That's not a thing. So the closest you can get was called an elliptic filter. But there's trade-offs. As you can see, this bottom one here, this here is called it's going up and down quite a bit compared to this one. So this is called base band ripple. So see, it's just got a much sharper, see N8 here, it's just got a much sharper roll off here for 8 than what this one's got, you see. But the trade-off is I've got more ripple in my pass band. So an elliptic filter will have ripple here and it'll have a ripple down here as well, whereas other filters won't. So it's all one big trade-off at the end of the day. So I'll put my bookmark in there because I use that page a lot. So in terms of filters, that or op amps, I've come to the end there. That's all I've got to share. So that's just really some of the most common design concepts I use. There are loads more. There are books written on this subject. And analog electronics. One thing which I've been doing with the AI work, which I'm designing, is I'm to do some work with sound and trying to do sounds in an ARM core with all the other number crunching. It was a lot of maths and it was getting quite overwhelming. And so I decided to design an analog filter. And then I just passed the result of the analog filter into the ARM core and did the maths on the result that way. And I've recently read that I know for AI, where you've got a lot of data to be processed, IBM are going back to looking at analog computers, which is all this op-amp stuff, which is what computers originally were. You know, it's only when digital computers came around, probably what the sort of 72, that sort of era. Before then, it was all analog computers, and all the maths were done using things that we've been looking at here this evening.
Steve, I think it was 1948.
1948.
Exact.
There we go. The same year that this thing was made. There you go. Have you just been looking that up?
No.
Oh, you just know it's 1948. There you go. Yes.
David Wheeler was my supervisor.
Oh, there we go. You see, that's the thing with Cambridge, isn't it? There's always someone who knows more about your subject than you do. That is the thing about this town. So look, so that's what I wanted to share with you this evening. Just before, just open the floor for sort of 10-15 minutes. The next session, I'll plug the next one. It's on, it's not Wednesday the 3rd of March because that's today. So hang on, I need to find my calendar now. Right, so the next one for your diaries is the 7th of April. Same time, same place. And the next one's on sensors. So, as I mentioned at the beginning, if anyone has anything they want to cover in sensors, then just let me know, and I'll do my level best to accommodate it. So, any questions or thoughts? Anything you want me to go over again from what we've been looking at this evening?
Back to the non-inverting amplifier. Well, in fact, all of them together probably. Where you've got resistors where the relative value is what counts, how do you choose the absolute value? Do I pick, say, two 1K ones or two 1 meg ones?
Right, good, very good question, John. So the way I do it is I usually start off like this amplifier here. I usually start off, this is just my starting, I'm sure everyone's different. I usually start off with the resistor here, the bottom one. I usually start off with 10 kilo ohms. Okay. It's an arbitrary value. That's because it's between 1 kilo ohm and 100 kilo ohms. And I'm usually looking to keep my values between that range. There are some devices. I mean, this data sheet example. Where was it now? Looking through all his notes. Yeah. So this one here. Yeah, I think it's that number there. Don't ask me how they come up with these numbers. But this device here, I used on a battery-operated device, and because it was such a low current device, that's 500 nanoamps, I actually had resistor values of, I think, 1 megohm. So it does depend on the device for sure. But to come back to the answer to your question, I start with this one being 10 kilo ohms, and then I'll work out whatever this one is. Yep.
Yep.
And so I then know what my ratio is, and then I actually get my resistor book out and I just see how close can I get to the ideal ratio for whatever resistors, which is why 11K and 13K works out pretty good for this gain of 1.84.
Yes.
Yeah, does that help? So start with that one, which I make 10K. Yeah, I then work out what that value is, and it'll be something odd. I won't be able to have it in the draw, so I then start sort of going through my calculation. 10K times 1.84. What's the next one? Have I got that? And I just find two that are as close as possible to the ideal value. It doesn't need to be spot on. That's not necessary.
Yes. What I was specifically wondering was, say, if you're doing it for a battery-powered circuit and want very low leakage through it, if you start putting really high resistances in there, do you start getting problems where it's too close to being open circuit?
Oh, right. Okay. I think if you have the values too high, I don't think it's so much close to being open circuit. This does depend on the device. If you take the old school 741, which is a bipolar transistor amplifier, you absolutely will not be able to use 1 mega ohm resistors. With this top one here, for example, which is CMOS, that's why it's down to just a few nanoamps. You certainly could get away with it, and no, it wouldn't be open circuit. However, the thing that I probably need to be cautious of, if your resistor values are too large, whilst it will work in theory on paper, I think there's more chance of being susceptible to, noise on the board is probably going to be a bigger issue than open circuit. So as I say, I usually hover, when I'm doing this, I usually hover values between 10K and 100K is my go-to range.
Okay, yeah.
Yeah, I mean, obviously, if you could make it, in theory, you could make it 11 ohms and 13 ohms, of course. The ratio holds, but I'll probably get a whopping current draw.
Right, but if you went, say, for 11 meg and 13 meg, are you then wandering into the too easy to pick up interference?
I think you'll probably have trouble performing as well with the feedback. I mean, the feedback, of course, has got an internal resistor here as well. Don't forget. Yes, that might be 10 mega ohms. So now your resistor, that will say 13 mega ohms, and that was the 11 mega ohms.
Yes.
Well, you can instantly see that together, that's about sort of 6 mega ohms. So you'd actually start to affect the gain of your amplifier.
Yeah. Okay. Yeah. Thanks.
But as I say, I think it's down to the device that you're using at the end of the day very much. Good question. Hadn't even thought about that till now.
You'd have to start worrying about inductance and self-oscillation as well.
Yes. Yeah, absolutely. Yeah, that's a good point. I hadn't thought about that. As I say, it is such a huge subject, isn't it? Amplifiers.
Hi, Stephen. Are you able to say anything about the efficiency of these amplifiers? I noticed in your selection criteria that didn't seem to be a thing. And I could be the wrong end of the stick. What I'm thinking about is with power amplifiers, the less good designs tend to be less efficient and get hot, even if they're not creating much distortion, as it were. Is that just not an issue with these op amps?
Well, I mean, with the op amp circuitries I do, like this one here, to bring it back into shot, you can see, that they really are specks of dust. So, there's going to be, they're only for small signal anyway. These aren't power devices for sure. So because these are small signal, that's not going to be a problem. But you're right. If you look at, I think it's D-class amplifiers, which are called push-pull amplifiers, which are used for driving audio speakers. They usually have a enormous heatsink on them. So, and yeah, they can become inefficient for sure and get hot. But I think some of those, they're probably the way to solve inefficiency, which is heat, is to basically either low signal. If it's high power, you just got to slam the power on or slam the power off, so you don't end up having voltage drop inside the devices, because that's how the inefficiency happens. But yeah, I think D-class amplifiers is the only one you've probably got to be careful of, which of course I haven't covered here.
Yeah, that's okay. This is op-amp, so that's I'm just trying to clarify. Obviously, the answer is doesn't really matter in this case. Yeah.
Not at the level which, you know, for signal analysis, you know, if you're doing multiplication, division, you know, if you're doing audio amplification to drive your speakers, yeah, I think then you've got to start to pay attention to inefficiencies and heat sinks for sure. It's all gone quiet. Somebody must have a thought.
Well, I was just thinking you just need to look at the static currents.
Yeah, I say it's very easy to get the design wrong. You know, everything looks great on paper, and then you go and make it. Yeah, and that's, you know, when you put the, you know, boots on the ground to make these things, that's when things start to go slightly wrong. You know, like clipping, for example, which we had a little look at.
A quick thought. You mentioned there was a very good question about how to generate negative rails.
Yeah.
And I've unfortunately missed the first one, but I'm guessing it's you were using some form of charge pump to create a negative rail.
Yeah. Tell you what, let me just try and find it for you. Just bear with me, and we'll look at that in a bit more detail. Bear with. Let me just have a try and get to it. If I go onto Silicon Cortex, we can have a quick look at how we can do that. So these are all available to download anytime. So say if you go to the website and follow,
I've just put a link in the chat.
Oh, well done.
Thank you.
Well done.
I was particularly wondering whether you could perhaps put up a rail splitter circuit so that you could, if somebody wanted to generate a plus V artificial ground and minus V for playing with op amps, it will be, I think it would be quite a useful thing.
Is this circuit sharing? Can you am I sharing the right thing with everybody here?
I can see something. It's moving before in front of my eyes.
Right. Okay. Fantastic. Right. I'm just trying to. Here it is. Okay. So this one here. This is it. So this bottom. I don't know if I've got a mouse on your screen or not. On my one there is. But U6. So this LM 27761. So this is 3.3 volts in. I'm sure if you look at the data sheet, for which the link is here in the schematic, it'll take you straight to the data sheet. You can just do a copy and paste on that, put that into Google, and it'll give you the data sheet straight away. And the output voltage is it's negative, and it's a ratio of these two resistors, that good old ratio again. And would you believe it? It gives you that negative voltage that we then want to drive our op amps. So you know, I've used this a few times for driving op amp circuits. So it's not one per op amp. You know, you can drive quite a few low voltage op amps off this. I know I don't think this design is particularly good for high current consumption. Wouldn't go that far, but you know, it's proven to be pretty bomb proof. So yeah, the circuit's there. If just grab it and copy it. It's no point reinventing the wheel.
Enough.
Easy. Good. Okay, let me unshare that then.
That sort of circuit's used in the Gsm RS232 chip.
Oh, is that right?
Yeah, they're just a couple of capacitors and it generates your negative rail.
Right. Excellent. Excellent. Yes, I think that there's the link as well, but you've probably already got all of that as well from. So that link there, which I've just put on there, is the link to the downloads. So you can just copy and paste that. And yeah, it can have everything. Just looking here, I should have made a note here to myself to look at chats. Yeah, so I think Ruth has now left us. Yeah, she makes the point here of the output being slightly delayed compared to the input. Yeah, there is obviously, you know, there will always be a fraction of a phase shift. I think that's probably more if you read that when we had the non-inverting amplifier up. Yeah, that's what I was talking about, like subtle phase shift. You only start to see those phase shifts when you start introducing capacitance. That's when you really start to notice it. So we'll make that a session in its own right, I think, later on.
Are you going to do a session on everything's a capacitor and an inductor?
You know what? Electrons is such a vast subject. You know, as I say, I've been doing it 27 years and I'm still learning things. In fact, to tell you the truth, every time I've been, you know, building these small circuits for us and testing them, I've learned something new every time. Thought I didn't know that before. So yeah, I'm learning as well as I build them. Well, look, it's 8:34. Has anyone got anything else anyone would like to add? Any requests for either, you know, for sensors or, you know, the one after sensors is going to be on reliability, which is EMC, my favorite subject. And the last one in July, I think, is on printed circuit board layout.
One sort of general question, which might go with sensors and also with power supplies, is if you want to have something which takes a reading every few minutes and takes basically no power in between, how do you arrange a very low power bistable, which will sort of flip on for a bit,
Yep.
Absorbing almost no power while it's off, and then gate power to your device, which will take some readings, send them on Bluetooth, and then go back to standby?
Yeah. Okay. So the way you do that, and I did that a couple of years ago for a project which was battery powered. It was actually for a fire door, where the tech went actually into the fire door. It was battery operated. So the way we did that, in fact, we actually did use the op amp that we had earlier, which ran on a few nanoamps. We had a 5 nanoamp real-time clock that could wake up a M0 ARM core. It then did a reading of the door and then decided whether it was then worth switching on the GPS system to send a signal. So the way to do it, you have to have something that's alive. But if you can get like a 5 nanoamp real-time clock, like with a wake up, however often you want it, to wake up the processor, to do a bit of number crunching, to turn something else on, to turn something else on.
So you'd actually have something digital doing that, rather than a very high resistance slowly charging a capacitor.
Oh, I see.
And then switching on at a certain voltage.
I think it depends on how frequent. Okay, I know what you're saying. I would say it depends on how frequently you want to turn on. So if you're thinking of just a few seconds?
Well, I was thinking of maybe once a minute or once every 10 minutes, that sort of time range.
Well, you'd probably draw more current doing it with a resistor and capacitor than you would with something like a real-time clock running on 5 nanoamps. You know, but I know in order to test your theories and everything's working, keep it simple to start with. Don't overthink it. Just simple is good. You know, you got enough problems with the software and everything else rather than trying to chuck something else in straight away. My pleasure. My pleasure. I was just looking at my clock here. It's 8:40. Has anyone got anything else I'd like to chuck into the melting pot?
Just to follow on from what you were just saying, there was a article I was listening to on the Hackaday podcast this week in the car about a design where an 80 tiny microcontroller was being used as a very low current process to do some sensor readings, and it would then wake up an ESP32 to transmit them. and then put it back, and then that will put it back to sleep. So they were using a much lower current, much lower power microcontroller to do the kind of the more constant work.
Yeah.
And then using it to wake up a more power hungry device that had features that were needed for data transmission. It seemed like a really neat idea.
Yeah, so that's exactly how you do it. I mean, this here just happened to have bits on my table around here. So this is a GSM module for sending SMS messages. This is really quite power thirsty, this thing here. So the way we do this, we actually switch the power off completely. And then, you know, which is how we did it with the fire door. And then when we want to do something, then we power it up. Obviously, you've then got to go through the whole reset sequence, make sure if the voltage is stable, and then you make it do its stuff. I mean, Bluetooth is quite power thirsty.
Yeah.
So yeah, no, if you're using the modules, well, or even the chips, yeah, they are very power thirsty things. And certainly if you're running on a battery, you know, you don't want to kill your battery too quickly, do you? Right, should we close there? See time's running away. Probably people gagging for cups of tea.
Thank you, Stephen. Another enlightening session.
Yes, well, it's my pleasure. I quite enjoy putting these together. So yeah, if whilst people are interested, we'll keep it going. So yeah, just before,
thank you very much.
Just to close, 7th, same time, same place.
Yep.
Just to remind you, Stephen, I'm still up for doing a KiCad PCB session.
Lovely.
Which would maybe nicely follow your PCB design session.
Yes. So yeah, so you're the expert on KiCad. I use Altium for PCBs, which is frightfully expensive, and I certainly wouldn't recommend it for any hackathon for a fact. Good. Right. Okay. Let's go and have a cup of tea, shall we?
Thanks very much.
Brilliant. Don't forget to download the notes.
Again, Steve.
My pleasure.
Thank you.
Okay. I'll see you all soon. Bye.
Senior to
Thanks,
15
bye.
years.